And you're thinking, okay, great. We can do alphabets. We translate them into numbers. What we want to do next is think, well, data is more complicated than just text and numbers. How do we arrange larger, more complex data that shows relationships and structure? And so that's our next activity, is to explore the world of data structures built on top of these foundational components. And this will be fun because some of you are probably very familiar with some of these schemes and potentially a lot less familiar with others. And so my guide is going to be the data structure stations that's linked, the first link in tonight's week of the schedule. So this will keep me on track. And so my plan is to do the simplest possible examples of these 7, and then we will experiment with encoding some spatial data. So the way that I set up the table is, once again, we have the world of data, things, I would say, external to us, external representations of the world in some form. Can you see that? Is that too high? Oh no, that's okay. And the way that I did my chart was, again, our big breakdown. We could arrange both qualitative and quantitative data in any of these kinds of structures. And these are the foundational structures that you will manipulate in whatever programming language you're writing in, whatever data manipulation process you're undertaking. You will probably encounter some subset of these various structures. So the way that I did this tree is I recombined and then split out to show that we can organize both types in any of these, in these structures. So some of this is mathematical language, some of it is unique to the data world. So a set would be any non-duplicate containing set, non-duplicate elements with no defined order. So a set is non-duplicate, non-ordered. So you can think of this as, how would I draw? A little sack of numbers, 12, 15, 18, 19. So non-ordered is important. This was supposed to be like the tie on a little sack. Sorry, that's looks like a very sad pepper or tomato or something. Okay. Ordered component, we often want to maintain the order of something. So a sequence is ordered, and we can cope with duplicates in sequences. So we think of binary as binary that runs through a computer has a fundamental orderedness to it, meaning we are sending ones and zeros from the beginning to the end in a particular order to represent encoded values. So I have binary as an example there. Now, this table is not trying to be exhaustive or as technical as it potentially could be, meaning I'm going to put list. List could arguably be a subset of a sequence. The important thing with a list is that we are thinking about the elements as indexed, usually starting at 0. So we can access the elements by index. And that feels differently when you're manipulating it than a sequence where all we can do is say, give me the sequence starting at the beginning, and then the sequence comes. A list allows us to extract based on index. So So we might consider these as basic organizational structures. I'm going to put them in outline in purple. And then we can get something a little bit more advanced. I need to turn my fan back on or I'm going to die. So the fun ones are what we build out of these. The next one we want to think about is a structure of data, rows and columns, our friendly table. We might also, the base form of a table we might say from math would be a matrix. And so tabular data, we would also call it dimensional data. So we have rows. What's another common name for row database folks?
Array?
Nope. We might be able to turn a row into an array, but from a tabular point,
Record?
Yep, we would often think of a row as a record, meaning it's often the case that a row encodes data, a single row encodes data about a particular instance of what we're storing in the table. So in my database for code enforcement, we have a table called person, in which each row represents an item, meaning a person, and then the columns, we would say, another name for a column would be a field. Or we could also, it's also known as an attribute, meaning if a person, that was a really awful way to do, to describe the table, sorry. So if we were, here's our table person. So what do we want to store about the person? We usually have an ID, and in database land and often in data structures land, the tabular data has unified types for each attribute. So we would say an identifier would be an int. So we would include both the name of the attribute as well as the type. We could put the name of the person depending on your database. You might call it char or text or character varying. Age, the int. Maybe instead of age, what would be better to store it? Not age, but
date of birth?
Yep, and then you can always compute age. If you store age, then your data goes wrong just by sitting there. It becomes inaccurate. So we would usually compute age. The date of birth, we would probably encode in some sort of date and so forth. So let's finish up the labeling that I did so poorly. So these, bunch of names. So column would be the spreadsheet form of the word, of the structure. We would also think about it as a record or an attribute. Part of this is just kind of learning the vocabulary of how the data world will talk about things. Programs might, depending on their history, use one or the other, but we're really talking about tabular data. And one of our projects will be to convert between tabular data and some of our other types. So table data is probably what we're most familiar with. And our journey continues.
I have a question.
Yes, please.
On your diagram, wouldn't column be more a field than attribute? Because the record has to be on the
field also. Were you saying that these aren't, or you wouldn't think about these as the same?
I wouldn't consider the column to be the record because the column is just all of the fields and attributes.
I'm sorry, yeah, record, I'm sorry, thank you. Good to have database people out there. These are the records. You're absolutely right. A record is a row. I got flustered. So row, e.g., not EG, AKA. Row record are these guys. And then columns, attributes, or fields would be the verticals. Thank you. Who was that? That was
Amy.
Amy, yeah, thanks. Okay, now our next two are ways that we can arrange data. A table is matrix-based, rows, columns. A tree is how we could organize hierarchical data. Hierarchical data. I should actually, we're going to start with the larger set, which is graph, and then we'll do tree in a second.
You're just slightly off camera, I think, right now.
Thanks.
Yeah, there you go. Thank you.
Good. So we're going to start with graph because a tree is actually a type of graph. So a graph is not this from math. A graph is a graph is a collection of nodes that are related to one another or linked. So a node, we would say related nodes of discrete values. Okay, so graph data, also known as network data, is fantastically useful. We see that social life and biological life involves a lot of interconnections and relationships between entities. So we'll explore one of those data sets in a moment. So a node, simply a discrete container in which we can put something. So I could create a network data of related individuals. So each node represents a person, and then nodes can be related to one another. So I should do the same. So I could do the people I am biologically related to, my parents, Cheryl and Craig. And this line that I'm drawing between them is important because that line represents some form of connection. And data structures can become arbitrarily complex. So we can attach, like a table, you can see where this goes, some of you are clever. We can attach attributes to both nodes and then anyone know what the technical name for the connection is?
Your website says edges, so I assume it's edges.
Edges. A node and an edge. So edges in this diagram suggest a connection between nodes. And so what you could start doing is you can attach attributes to nodes or edges. So if I were trying to make a graph of my human connections, I could say edges that I shade here are purple are biological connections. And then I could continue adding to my network of human connections with different colors. So I have a housemate. So housemates would be blue, and so forth. We could do the same thing with the individual nodes, and we could come up with a set of attributes or information that we attach about each node in the network. And maybe we want to explore how this is used in the data world. So if you'll join me, I'm going to do a screen share, but I'll come back to it in just a second if you are behind. So I put a link up to a cool nonprofit. One use of network data is one group. If you're a 1984 fan, the organization is called Little Sis. It's a free database of who knows who at the highest, or the heights of business and government, which is exciting. So what this organization has done is built a graph of individuals and organizations that have influence in our society. So who should we try? What's a
Donald Trump.
I don't think I'm ready for that right now. How
Okay.
about Elon Musk? We'll see if he's got any connections. So you can see network maps, and this will actually draw, oh, look, here's a graph of connections. So we can see this, just what we talked about. Each individual or organization, this is unfortunately is not a particularly great graphing application. This is an open source tool. I actually met the folks that run this. That's why I use it. I try to use things that have some connection to. It's an open source project. You can actually contribute. So it'd be kind of fun to help them. It'd be neat to get all these color coded based on the types. If I hover, you can see they're trying a little bit. They have solid lines, and this node or this edge has a label associated with it. Elon Musk is a major shareholder of Tesla Motors. This edge suggests, we can't quite get to it. Maybe if we zoom in a little more. So yeah, they've got some room to go on their UI. I guess the solid line is insider. And so one important thing about network data is we can have interrelationships. In this case, these edges are directional. So we can have different types of edges. So in this case, this arrow is suggesting that Elon Musk is an insider of Solar City, and not the other way around. We would not say that Solar City is an insider of Elon Musk. So directionality can create another layer of encoding inside our data structures. And I have an exercise that I think we may be a little bit too busy to do, but I'll propose it at the end of the class. So and if we click on the individual nodes, we can then explore their own individual graph. Let's try Mr. Gates. So he's got, how do we get back to our Explorer? Interlocks. Here's our graph. So here's would be, you can actually contribute and add connections to their system. And he's got a lot of data in on him. Why did it not give me his graph? How did I get to his graph? Oh, I have to scroll down, I bet. It's down under his. There it is, network maps. So they are not mapping all of his connections. This is probably, I'm almost positive it's truncated. So yeah, so Bill is not, so it looks like what they've done is they've made subsets of nodes in maps. So I bet there's a bunch of, they've made a bunch of maps that he's a part of. UNICEF, the Gates-Clinton map. Let's look at that one. Ah, there it is. I was looking for an interesting property of maps. So we could describe movement through nodes by following the edges associated with each. So we can see we have a forward arrow going from Bill to Hillary with contribution, and several point in. Sylvia Matthews Burl goes out. I'm looking for cycles. I don't see any in there. This would be fun to explore. What I'll invite you to do, if you want, is to actually create a network data set of a aspect of your life that you're familiar with, and we'll see how we can encode it. I'm going to go back to my board here. An important feature of maps is my father and mother are married, so I can make an edge for marriage, and most notably, if I start at Eric and move to Cheryl across an existing node, I can then find my way from Cheryl to Craig through a node, and then find my way back to Eric. So what's important is graphs are related nodes of discrete values, and at the most general form, cycles are allowed. Cycles allowed, meaning we can get back to an original node by following the edges. A tree, by definition, is a graph in which there are no cycles. So a hierarchical form of graph might be your classic organizational chart. So at CCAC, a graph has a root node. By definition, a tree has a starting point, a root node. And then we describe in graph theory, a related node is called a child. It's actually, they use human family organizational terms to describe these. So these would be provosts. So there's like, I don't know the strict names, I used to. Academic provost. I don't remember what the other ones are. But then I have a dean. That's still on there, sort of. So I have a dean. And so trees come in a variety of flavors. The tree is extremely handy for a variety of reasons that we'll examine in a little while. Let's just label these so we don't get ahead of ourselves. So root node, these would be considered children of a parent node. So parents are up and children are below. Anyone know what we call nodes that do not have any kids, if they have null kids? It comes from the forest, not families. What's at the edge of your branches?
Leaves.
Yep, so a node by definition that has no kids, it's called a leaf node. And if you take a data structures class in a computer science program, a good data structures class in a computer science program, they will ask you to code up a tree in which you represent each node as an object, and the objects contain pointers to kids. And so you can write algorithms that traverse, the word is traverse the tree in various ways. And so there's clever ways to write code to traverse trees in a variety of ways. If you're the curious type, we can there's a whole world of information about tree data structures, because they lie at the heart of almost a lot of our computer programs. So a tree traversal algorithm is a way for moving through nodes. We're often in a position of having data that is organized in a tree structure, and how would we access or print out or share data in that tree? Well, we have a variety of ways of doing that. So you can explore these in a great deal of depth. But you can see at its foundation, where I want you to start is just starting to think in these terms of nodes and directionality, and then as you are interested, oh look, here's the pseudocode and how to actually write various traversal algorithms. So these are, people get sucked in by graph theory. There are people that the main algorithm data structures book, there are people that will go through and do all the problems and share them out because they love doing this so much, because it's so clever. A variety of trees exist. The most common tree is called a binary tree. So I'm gonna make this a little bit messy. So types, a binary tree is the most common because it's used for searching. So a binary tree is a tree defined as one in which each node can have up to 2 children and not more than 2 children. We can also describe trees. The particular flavor of binary tree is called a red-black tree, which involves a specification about the balance, the relative balance of the branches of the tree. So as we add child nodes to a tree structure, the tree's balance changes. And certain definitions of trees can specify if you are adding nodes in an uneven way, you actually have to reformulate the tree and reorganize it for searching. And I'm not going to spill all the beans on how that works just yet, because it's quite cool, and I want to do a whole exercise on it. Are we missing, what's our last one? Ah, yes, maps. Our last structure, let's go over here. We're gonna make this not a tree anymore. It's gonna be more like a timeline. The last type that you might encounter is a mapping. And so these are key value pairs in which the keys are searchable and the values are connected to those keys. So a common way of thinking about mappings would be settings in a particular program. So we could have a key would specify what the setting is. So maybe in Zoom, I'd have volume level would be the key, and then the value would be some percentage, 78. User, my name is E. Darsow. And so those key value pairs are organized such that the keys are searchable. I'm running out of room. Let's put this up here. And this up here. And so you can still see this. So keys are searchable. So we look up values by key. One common, probably the most common key value pairs that we're familiar with, even if we don't know that that's what's going on, is the web pages. So if you're in my browser, hit F12 on a Mac, command something. It's called Developer Tools if you go up to menu. So if you look in F12, if you look in the developer console, I'm going to split this out, separate window. Key value pairs are used extensively in defining the structure, and I would say that not the structure, the display of features on a web page. And so one of the interesting parts of this is you can play with mappings right away just by tinkering with the display data in a browser. So what I'm going to do here is we're seeing the HTML code, and then I'm here, and this is, what is this? This is Firefox. So the display components are key value pairs. So the width of the box in which I put stuff is the key. The value is 800 pixels. And so I can, modern browsers are super neat because I can change the value on the fly and the page will actually reformulate. See how it shrunk? If I go down to 200, it automatically changes on the fly and squished all the text in. This is fun for designers because you can actually come in and tinker with other people's web pages. It doesn't save on the server, but you can take screenshots of it, and I'm sure you've seen this on the internet. People do this quite a bit. So I can add a background color like green. Woo, look at that. So key value pairs are a way of storing data that we use in programs constantly. And so a mapping would be considered a set of key and value pairs that we can move around as a group. And this is in fact why a mapping is so handy, is because I can convey information like display quality and then value and put all those in a map and ship them with a web page and say, hey browser, here's the map on how to display this page. And it will traverse the keys and look up their values and follow the instructions that are in the value.
There are also web programs that let you change this with like a little widget. Like I personally use Dark Reader, which automatically puts websites into quote unquote dark mode. And it's much easier on the eyes.
Huh. So yeah, that's tinkering with the style mapping, the CSS mappings of the web page. That's a great example. So there was a crash course in data types. Now, if you hit F5, it'll go back to its normal structure, but you can throw people off. You could send someone an email and say, "Oh my goodness, your formatting is all off," and they won't know what's going on. So this took about 20 minutes longer than I expected. So let's take questions first of all. Turn off the share, and then I'm gonna do a little reflecting, and maybe we can do a vote. I have an exercise related to spatial data encoding, and I also have an exercise related to tree table manipulation. Let me just think for a second. I also want to get to our strip surveys. So let's take a simple yes or no vote for now. So grab your participant box, and in that participant box you should see a raise hand. And so I'm going to chat this out. I know there's a poll feature, but you actually have to go in and set it up separately, and I want to be expeditious. So let's raise your hand if you'd like to do a hands-on data structures exercise. and push back strip surveys to next week. So oh, yeah, we're getting some hands coming up. Oh, good. You all like data structures. That's fun. Okay, we've got some neat things to do with that. Okay, so for on your, we're going to take a longer than normal break because I'm going to get us trying this activity to see if we can. We're going to learn how to encode network data in a table and see if we can then reconstruct it. So what I'm going to ask you to do on your break is choose a network of something you're interested in. And some examples might be, so here's your to-do on break. So I want you to create a network. So not a tree, meaning you can have cycles and you can have multiple nodes linked. You can have one node can be linked to every other node and so forth. So create a network of nodes about a content of your interest. And say, I'm going to suggest maybe approximately 10 nodes. I would never dream of limiting the number of nodes in your network. So if you want to overwhelm your peers, you can make a more complicated network. So some ways to think about this, you might, if you like film, you could choose an actor or actress as a center node, and then any other actor or actress that they've acted with. If they've shared a film, your edge could convey, so edge means starred together in film. So in our case, Matt Damon shared with Jessica Chastain. Sad part about the Martian film is that the script is terrible. The lines are really bad. So it's kind of an unfortunate film to be so cool, and then it's almost hard to watch a second time because the script is so bad. So you can start making a network of that. You could do musical artists that have shared a role in a band or a concert. You could do oh, so many. Any other ideas that come to mind right away? I don't want to pollute the waters. My ideas.
I'm thinking like some kind of leadership hierarchy.
Yeah, so if you want, you could certainly make a tree. A tree is a subset of a graph. So you could also make a hierarchical data about if you have an organization that has a tree. One of the interesting things people do as consultants in organizations is they make a hierarchical data structure of the formal leadership, and then they do a bunch of surveys with the employees, and they go back to the folks that hired them and say, this is the informal network of relationships of strength within your organization. One of the things you can start doing, so as you think about your network, you can come up with maybe a more complicated, maybe not more complicated, but you can type your nodes. So maybe lead roles get a certain type of color. Now you can, I'm just using colors because I have markers here, but you can just store them in, you can store the attributes in the node itself. So we could say this is a star role and this is a supporting role. You can also give the edges attributes like weight. So maybe you write a program in Python that goes through and ingests the movie scripts of a bunch of actors and counts how many lines they say to each other. And you give a numeric weighting to the edges. So maybe the number of lines that they had speaking to each other, they only had 18 lines in this film, but in Interstellar they had 73. And then there's interesting software packages that allow you to visualize it, and you can change the weighting of the edge based on the attribute that you attach to it. And I have a link to that piece of software in our schedule. It's pretty cool. So let's take a little bit of a longer break. Questions on what I'm asking you to do? It would be helpful if you do this in a way that you can upload to our shared drive. So if you have a easy way to take pictures, that's great. You can also do it in, an easy way to do it is in draw.io, which is a Google Drive tool. If you're logged on to that, works really well. So in Google Drive, you can say new, more, and then diagrams.net allows you to make maps in a clever way. Language preference. Okay, that's good. They actually used to have a much broader terms of use, but they only asked for your email address, language preference, and profile picture. So that seems that's reasonable to me. Personal info made publicly, view and manage file. That's not great, but I trust them pretty well. So this is a cool tool because you can just make nodes. Is it the Martian? There it is. So we could say he was really good. Look at that last name. That's great. So we could say so this is a pretty easy tool. And then you can just connect them by clicking and dragging on the edges. So however you want to do it is fine. Questions before we take it? We'll take a break for about 20 minutes. Verbs to describe the connections rather than the number. Absolutely. So your verbs, I could imagine a program could code the edges based on the verbs that you use. So yeah, your attributes can be any data type you want. It could be numeric or text. Absolutely. Other questions for the group? No, it doesn't have to be people. Could be things, species. You could do an interesting thing if you just want something really simple is the structure of the stuff in your room. So if something is on a table, it becomes a child node of the table as a parent node. You can do all sorts of stuff like that. Okay, I'm sitting at 7:34, so let's go until 55. That's about 20 minutes. We'll check in then. I'll keep my speaker there. So once again, as I'm talking, feel free to chat out, and there's lots of nice folks out there that can help debug on chat if I'm up here flapping my hands. Okay, so nice clean board. So the next phase of the activity, which is the cool part, is we want to figure out how a computer thinks about these graphs, because once again, the computer doesn't know what a node is. It doesn't know what a little line and a bubble is. So we've got, so this is at a high level. what we want. So we want a, so these are human symbols, and we need to make it over to zeros and ones, because that's what gets stored. That's the only thing computers can deal with. So we need to end here. And so the question becomes, what kind of representation can get us there? And this is where tables come in. So the point of this exercise is to realize that, or not realize, but to experience how data structures are translatable between formats, and a data engineer would be someone whose job it is to move around data of various formats, of various encodings from different places. Usually a data engineer will do a lot of the moving and pipeline building, and then an analyst, once it gets to an end location or a repository, can then start doing the crunching. So we're doing the kind of thing a data engineer would think a lot about. So let's, I'm going to do a quick example with my little graph, and it's fun because I can see the complexity growing among people's graphs, which is cool. So I did musical influences, and the way that I built this out, I was kind of curious what Wikipedia would help us with. So Little Richard died not too long ago, and so I've been listening to his, WIP did an hour-long special of some of his influences. So what I did was I looked at the associated acts associated with Little Richard, and I'm going to go back to my board here. That's where I'm drawing some of the data from. And music is kind of fun because the process of hearing and making music is very much a network kind of thing with interrelationships. So I'm going to do just 4 nodes for the sake of brevity. So I started with Little Richard, and I saw that one associated act was Rolling Stones, the Stones, and that took me to associated acts of the Beatles, and both the Beatles and Little Richard had Billy Preston as an associated act. And his photo on Wikipedia is great. Okay, so I've got a little network. Graph theorists, there's all sorts of interesting metrics that you can come up with even a simple graph. So how many nodes? We've got 4 nodes. We could start asking density, so we can count up how many edges are attached to each node. So I can just count these. So right now we have a symmetric graph with each node has 2 edges. So you can start calculating node density and say total nodes, say nodes over edges for a simple metric. So we've got 4 nodes, and 1, 2, 3, 4, and 4 edges. So we have an edge density of 1. So there's all sorts of metrics that you can start using if graph theory gets you going. There's a world of exploration. So I'm going to leave it here without anything fancy. That would be interesting. You could write some cool code that could start thinking about directionality, because if the time periods don't overlap, someone in the past couldn't use a future act as their influence because they haven't existed yet. So that's where some directionality could come in, and you could start being clever about how you represent that. But for now, Wikipedia just said associated acts. So it's an undirected edge. So we would say this is an undirected, I need to work on my capitalization, undirected graph. So let's turn this into something closer to binary. Well, we have to preserve the structure, so we've got to do something more than just translating each letter into a binary value, because we're trying to figure out how to show that Little Richard is connected to the Stones, but I did not find a connection here. So we're going to start by making a table, tabular data, in which every node has both a row and a column named after it. So I'm going to do that here. If you're a spreadsheet whiz, this is certainly something to do in a spreadsheet. Stones, Preston, Beatles. I think this stuff is wicked cool. So then we're going to give each one a column. Can I zoom out anymore? Come on. Yeah. Oh, good. All right. So then this is nothing. So okay. So we have cell values that we can store data of arbitrary types in. And so what we're doing now with this particular exercise, as far as I know, there's not some sort of unified standard of graph to tabular encoding, but rather a piece of software like Gephi that I linked in the schedule. A piece of software would have its particular way of doing this kind of thing. And Gephi is cool because you can give it a table, it'll make you a graph, or you can give it a graph, it'll make the table. So what I'm going to do is just start with a node. Often you'll find nodes, because they're stored in a data structure of some kind, probably a database, they'll often get an ID. So I'm just going to number these arbitrarily, so we can remember that they're often going to have some sort of absolute ID to avoid name clashes. So I'm going to start with the row and ask, okay, is Little Richard connected to Little Richard? Now, in this case, in graph theory, you can have self-connected nodes, but we're not going to get meta enough to ask, was he influenced by himself? So we're going to say nothing in here. So an encoding scheme would say, we'd make a little key for what the cell values refer to. So a common way to do this in a database would be, if there's no edge, we would encode that with a null value. So we could say null, which is the word suggesting nothing there, no object. Is Little Richard connected to the Stones? Yes. So in our case, because we're not encoding anything fancy, we're just going to say on or off, yes or no, edge or no edge. So edge equals 1. Is Little Richard associated with Billy Preston? Yes. Is Little Richard associated, according to Wikipedia, with the Beatles? No. Stones. Is Stones connected to Little Richard? Now, here's, because we're doing an undirected graph, what we'll find is this, the unity line through this table will not be used. So we will say, we will say that all of these are not connected to themselves. And then because it's an undirected graph, we will put nulls in these, and I'll explain why in just a second. Oh, nope, need that one. Because right now there's, because this doesn't have an arrow on it, the only thing we can have is, are these connected or not? So notice that Little Richard connected to the Stones could be coded here or here. So if it were directed, meaning we had record of one artist actually drawing on the music of that other person, it might be the case that the Stones drew from Little Richard, so the direction would be like that. So what we could do, if you get someone's graph that is directed, you'll have to think about, you'll have to label your axes. So this would have to become a, you could say this is a from and a to. So it would work like that, but we're being simpler here. So we're not going to use those. So we're going to ask, is Preston associated with the Stones? No. Are the Beatles associated with Little Richard? No. Are the Beatles associated with the Stones? Yes. Are the Beatles associated with Preston? Yes. So if we wanted to check our graph, we could sum the columns and check to make sure that we got everything. So 0, 1, 1, 2, and these all sum up to 4, 1, 2, 3, 4. So we got all the edges. Now we're getting a little closer to ones and zeros, right? So now we've got a table. This feels more computer-like because we could imagine how could we encode a table? Well, a common feature of spreadsheets, which is tabular data, is to allow an export of that data. So I'll show you an example from a pre-COVID class. Hold on here. Here. These are cool. Wait, this one's old. Google OneDrive is significantly better than, or Google Drive is significantly better than OneDrive, but we'll leave that for another day. So one of my students, actually one of our graduates from the data program, created this undirected graph in a spreadsheet, and this relates to directors and actors and their relationship. So we can see this tabular representation. Now, in this case, the value of the cells starts taking on attributes. So a 1, it's not just edge or no edge, it's what kind of an edge. So depending on which graph you choose, you may need to encode your table in more of a clever way. So most spreadsheet programs, the 3 major ones, allow you to export. So we can, oh, it's just going to give me an Excel. Let's do a file, save as. I'm going to grab it as an open document. This is amazing. For most of Microsoft's career, existence, they refused to be compatible with the open document format. Even though it was a free and open source format, they said, no, we will not let you export in an open source format. And now they took over and they have to do it. So I can export it for open document, discard, yes, save, sure. Okay, so here it's on the local file, and so I can come up and say export, And so how might we export this? This is cool. So we can say, I want to export it as, oh no, where is it? File. I think it's just save as. I want to save it as a text file. So this is taking from tables and turning it down, or turning it into something that's a little bit closer to binary. So graphs, and so we'll say Hitchcock. Now notice this is a common way of storing structured data in a text file, CSV, comma separated value. So I'm just going to call it Hitchcock, and we're going to say use CSV format. This next screen is super exciting. So if you're not looking, you should look. Huh? Look what it's letting us choose. Look at all those character sets. These are the encodings. So OpenOffice has built into it the chance to say, well, how do you want me to save the G on Grace Kelly? What number do you want me to use for that G? How do you want me to translate G into a transferable number? And when in doubt, what do we use? Unicode. And the next thing it's going to ask us is, the way that it's going to export this is it's just going to be a computer. It's going to take the first cell, and then it will put its value into the file, and then whatever delimiter or separator I choose, it will place that separator and then move to the next cell, copy that value into the text file, and then put a delimiter, and then move to the cell to the right, copy the value, put it in the file, and then the delimiter. We can tell it string, another name for text. So it's often, some programs will require double quotes, some don't care. Double quotes is most common. And we have some interesting options here. I'm going to say quote text cells because I want you to see how that works. So that's exporting. So now we're changing structure from tabular data into a flat file that has, that's basically a series. Just a bunch of data with separators in it. So now let's go look at it in graph. This is great. Look, watch this. Look at that. So this is a more transferable friendly version of this table. Let's put these side by side. So notice, why is there nothing and then a comma? Because this cell had a nothing. It had nothing in it. And so then it moved to it put the delimiter, comma, and then it copied the value. It said, this is not numbers, so I'm going to put it in quotes. So it automatically quoted it. That might, if you're reading into a database, they'll often want quotes so that it knows that this space is part of this whole value, Alfred Hitchcock. That would be very common. And then the X's, once again, was Stephanie's code for a nothing. And so if you are reading this file into another tool, a lot of database programs will allow you to specify what is the null value, because you'll often get a file where someone put in something weird for null, like X. You'll also see a -9 or a -1 for a nothing, and so you can usually tell it how to translate a certain value into a different value that's unique to that system. So this, we could imagine, we could figure out how to store in ones and zeros. Now, notice one last thing. Will you show me all of them? Sorry, I always forget where it went. I want to view non-printing characters. I'm sorry. When in doubt, documentation. I bet it's in the settings. Dry white space all. Okay. Is that it? Okay, sorry, it looks more complicated than I thought. How does the, we could then take this and put it back into a spreadsheet, and we'd ask the question, well, how does it know when the rows start? And that's because we have, at the end of these lines, we have an invisible non-printing line return at the end that we cannot see in this particular view. I could have sworn there should be an easy way to do that. Sorry. Let's see if I can do it in mousepad. Good. Okay. So when in doubt, use a simpler tool. So if I open this text file, I can say edit. I just had it. View. Line endings. But I just saw it. Select. Display line endings. There. So you can see embedded in this file is the return character at the end of the line. So by being systematic from the spreadsheet, we have now encoded tabular data in a text file which is program neutral, and we could see that we could slurp it back up in a spreadsheet. So we'll see if we can, I'm going to close this and then see if we can say open file. And spreadsheet programs know how to read in CSV, so I can say, hey, look, spreadsheet, look, here's the character set. Again, it has to figure out how to interpret the underlying data. How do I turn a human character in? What do I turn the numbers into using which table? And so I can see I'm telling it my data is separated by commas, and it looks like it already figured out that quotes were for strings. And so we'll see if we can get it back in. And there it is. We can clean it up with a little bit of cell alignment, and that looks pretty good. So that's a tabular representation. So pretty neat. So what I'd like you to do, and we'll close out with this, and we'll check them next time because I want to give people some time to do this thoroughly, is what I'm going to do is let's come back here to graph representations, and I'm going to make a new folder. This is all kind of, we have to COVIDize all of this. So yours are in here. So I'm going to rename this. I hope I don't blow anything up. Come on, Bill, don't fail us. So I'm going to say Fall 2020 graphs. And now here's the key to make this interesting is I want you to choose someone else's graph and make a table out of it. And then next week we're going to see if we can reconstruct the graph. So this is tables anonymized. So in this case, do not, no topic, or creator, because we want to see if we can go backwards and get a representation of the graph back. So let's put this, let's write this in our master sequence. So for this week, so we're basically doing this home practice. This is pre-COVID. So this is fall 2020. Again, this is how not to run a web server. Do not edit the files directly on the server like this. It's headaches only, but it's awfully convenient. So your to-do list will be finish your graph, upload to OneDrive. Then choose a graph that's interesting to you and create a tabular representation either on paper or in a spreadsheet. We want to try to encode as much of the original data as you can, i.e. are the edges, do the edges have additional meaning beyond just I'm an edge? Do the nodes have values? Do they have types? So maybe someone has people and things in the graph, so maybe you could even infer some types. And then we want to save your tabular representation using only your first name, not the name of the creator. Save it in the special directory called, what did we call it? This. Rename. That is the ugliest directory name I've ever made to this date in my life. It's called DAT. And then, and that'll do it. So then what we'll do next week is we'll start with an activity of, I'll cook up more than just make the graph back, but we'll use that as the raw material for next week. And then I'll just say, in case you didn't get a chance to finish your strip survey, if you didn't make a strip survey, finish that and upload in the link above this cell. Okay, and now magic. Everyone get your finger ready over the F5 key. Everyone ready? It's very exciting. Here we go. 1, 2, boom. Cool. Okay, so there's our to-do list for the week. And this is pretty neat. So if you're the kind of person that knows a lot about this stuff, you know, challenge yourself. One way to challenge yourself is to go and grab Gephi and see if you can get it installed. I think the Windows install, it runs on, I think it's Python. I think it's built in Python. So if you're feeling unchallenged, if you come to our schedule right here, Gephi is the open source program that lets you make graphs. You can do some really neat things. One of our students was a research assistant for a doctor and decided to do some cool stuff. I think I have her project. It would have been ketamine. There it is. So Lisa actually used Gephi to create network data related to publications related to the therapeutic use of ketamine. And this is the real deal. So it turns out when you graph human systems, what you tend to find are a certain ratio of kind of center main thinkers and then peripheral nodes around it. And so, of course, companies use this for marketing purposes extensively. Facebook, that is the economic engine of these social media tools, is selling network data about people to companies and say, if you were going to mail out free samples of your product, who would you mail them to? Well, you'd mail them to Zarate C and Charney D and Matthew S, because they're connected to the most people. So you can get the most bang for your marketing dollar if you are smart about network graphing. So she did some cool stuff with Gephi. So if you're feeling unchallenged, you can try to cook up Gephi, and there's some good tutorials on how to do all that. The sky's the limit. As long as your RAM can do it, Gephi could make graphs of very dense data.